Okay. Good evening, everyone. Everybody. Uh, Before we get started, I'll introduce myself to all the participants. I'm VVS Murthy, a PhD student, currently in my fifth year at IIT Madras. I am one of the teaching assistants for our NPTEL course on kinematics of mechanisms and machines. So before we get started with interacting, I would like to know because there are only four participants today. I would like to know your background, whether you are from pursuing your undergraduation or you are in your post graduation or you are from industry background. So uh, I'll read out your names. Maybe you can unmute yourself and tell. Otherwise, I would have, if the participants were more, I would have put a poll. But there are only four participants. So, Mr. Manikandan, Manikanda Raja,
Yes, I
can you
am
tell
Raja.
me whether you are from UG or PG or from industry background?
I am working as a SS scholar, sir,
Okay,
at MEFCO School of Engineering College, Sivagasi.
okay. Uh,
Due
yeah,
to my interest, I am studying this kinematics.
yeah, nice. We have another friend who says, who's Perumal Sami Gurusami. He's also a research scholar. Nice. Uh, Venkat, can you unmute yourself and tell me your background so that our interaction becomes better, so that the level at which we need to discuss the subject becomes easier. I'm unable to hear you. Maybe you can write a comment. Okay, we'll get started. So there are three important terms, as our name of the topic suggests, name of our subject suggests: kinematics, mechanisms, and machines. Kinematics, we'll define it in this fashion. We are well versed with this term since our 11th and 12th classes, where it is a study of the motion of particles and rigid bodies without reference to the force causing the motion. Okay, so we do not give respect to the force that is causing the motion, but instead we are interested to study how a motion of particles or rigid bodies move. Here there is one more term which we want to define, that is rigid body. A rigid body is can be defined as a body where the distance between two consecutive points on that body do not change with respect to any amount of force that we apply. Uh, to just a moment. To Okay, so to elaborate on my point on rigid body, for suppose I say that this body is a rigid body. What I mean is, we have points A and B marked on this body, and suppose we apply certain force F or a torque that causes rotation uh, about one of its axis. So the definition of rigid body goes this way: whatever F magnitude of F or direction of F, and whatever magnitude of torque or direction of torque that we apply, the distance between A and B remains the same throughout its motion. That is what we mean by a rigid body. Uh, so the next term, uh, somebody posing questions. I'm from Guntur. Okay, fine. Yeah. So the next term is mechanism. So mechanism can be defined as a combination of rigid links or rigid bodies, which the rigid bodies we are going to call them as links in our subsequent discussions. They are so shaped and they are connected in such a fashion using different kinds of joints like revolute joint, prismatic joint, etc., which we will study later. They are connected to each other so as to transfer and transform motion or forces from input to output. Many of you might have learnt about uh, heard about a slider crank mechanism. So you can relate whatever that I am talking about to the slider crank, a simple slider crank mechanism, and or a 4-bar mechanism, and relate to it. For students who are or participants who are new to this subject, we will learn this in detail later. So a kinematic linkage is the one which is made up of rigid links. So can somebody give examples of mechanism that we come across in day-to-day motion, day-to-day life? You are free to unmute yourself and ask. This is an interactive session for 2 hours. So previously it was of 1 hour during previous semesters, but now it has been increased to 2 hours. So our discussions can be more elaborate and we can have more time. So can anyone unmute and give your answers on or examples on what a mechanism is? Okay. One of our friends says umbrella. Okay. Any other answers?
Cam and follower.
Okay. Another friend says it is cam and follower. Okay. We will discuss about those things later. So I'll give you one other simple example. It is a watch, not a digital watch, an analog watch. The seconds, minutes, and hours needle. So they are connected at one joint and they move relative to each other for the sole purpose of motion transformation. So that falls under the definition of mechanism. So third one is a machine. Most of us should be able to define machine. It uses mechanism or a combination of mechanisms to transform motion and force from power source to perform some mechanical work. These examples which we come to know, which we see daily, are some lathe machines, milling, drilling machines. Over a course of 150 years, we have uh, science has developed so many machines that we all know. Okay, uh, I'll give you some more examples before we get into solving numericals. I would like to discuss few applications of mechanisms. The first one is a vice grip. So a vice grip, you can see on the left side of the screen. Uh, we can hold the vice grip here and we clamp uh, whatever object we need at this end. So this is actually a force multiplier. We know that the mechanical advantage of such machines are more than one for force multipliers, which we'll come to know in later stages. The second one is an interesting one. It's an ornithopter mechanism where uh, it's a combination of three mechanisms that I have told you in my previous slide, that it can be a simple mechanism or a combination of mechanisms. So it is a combination of three mechanisms. I'll define first what an ornithopter is. So suppose we want to do a surveillance of uh, a sensitive area, say a military area, where we don't want our foot soldiers to go and have a surveillance in person. So what we do is uh, we can design an ornithopter mechanism such that it can fly and it is camouflaged in a fleet of birds. So we have a fleet of natural birds, and inside that they camouflage this ornithopter mechanisms and send for a surveillance. So obviously, which we see today as drones. Uh, so they have a surveillance time, say 30 minutes, 20 minutes for each drone. So they can click few pictures and come back to the security forces and have a picture of what exactly is happening there. So we have three mechanisms that I have told you. This is one 4-bar mechanism here, another 4-bar mechanism it is attached here, and this is a cam and follower. Uh, we some of us might not clearly visualize these three mechanisms at this stage, but I would like to describe this so that we all can appreciate what our subject is capable of delivering. So, okay. The third example is uh, for automobile enthusiasts. So we have a suspension mechanism. There are different suspension mechanisms like McPherson strut, etc., etc. So the main purpose of the suspension mechanism is to isolate the chassis or the roll cage from the bumps of the ground. So here we have two different mechanisms, one to the left side of our steering wheel and to the right side of our steering wheel. So uh, even suspension mechanism is also a mechanism which we come across our day-to-day life, and that is also one of the applications of our subject. We'll define few other terms. Uh, Firstly, I would like to define a planar mechanism. A planar mechanism is the one where all link motions are in parallel planes. That means uh, you can visualize the motion of each of the link in parallel planes or a single plane. Uh, Example could be an excavator where all links, whatever we see here, this is a prismatic link which has a sliding degree of freedom. Uh, and here also you can see that all links which are connected only are in parallel planes. So such kind of a mechanism is called a parallel plane, planar mechanism. And in real world, we also need spatial mechanisms where the link motions cannot be restricted to just uh, 3 degrees of freedom. We need to have 6 degrees of freedom for few links. So such mechanisms are called spatial mechanisms, and the link motions uh, are not restricted to just parallel planes. They can be out of plane also. So one of the example could be our parallel kinematic machine, PKM machine. Uh, you can see it's working in some of our YouTube videos also. Okay. So next I would like to discuss about the type of links. There are basically three kinds of links. The first one is a singular link, binary and ternary links. A singular link is a link which is connected to just one other link. A binary link, as the name suggests, it is connected to two other links. A kinematic chain, which is just consisting of only binary links, are called a simple chain. And a ternary link is the one where it is connected to more than two links. Okay. Uh, we'll define what a kinematic chain is. A kinematic chain is a combination of interconnected links, okay, so as to perform uh, transfer motion from source to the destination. Okay. Next, we will define one of the other important term called degree of freedom. So, degree of freedom is the number of independent variables that need to be specified to fix the configuration of a mechanism. I think you have already solved few problems on assignment problems. So, uh, if somebody has some questions to ask, in the theory part, they can ask me now or at a later stage also. If nobody has any questions, we will start with the first question. Assignment 1 का solution. Assignment 1 solution, solutions for all assignments, they'll be updated in our NPTEL portal itself. You'll get regular emails for it. Okay, Harish? Harsh Prem. Okay. Uh, I'll give you a couple of minutes time to work the first question. In a planar kinematic chain, we have two
सर ये
statements.
क्वेश्चन
Sorry?
सर ये क्वेश्चन हम लोग के असाइनमेंट का नहीं है
Yeah, uh, uh, I would like to speak in English because it's the common uh, mode of communication. I think you will be comfortable with it. Uh, we are not going to solve uh, questions that are from your assignment. Uh, we will be
सर
discussing.
प्लीज़ सर सर प्लीज़ सर अ, हम लोग
No, we
सॉल्व
are.
किए हैं सर लेकिन हम लोग एक बार कंफर्म होना चाहते हैं सर
Yeah, you
असाइनमेंट
will.
में ही जो
I
आया है
understand
वो
your
वाला सॉल्व
concern. You,
करवाइए ना प्लीज़
who is speaking? May I know your name?
सर हाँ मैं हर्ष प्रेम
Harsh Prem. You'll be given the solutions for your assignments and they'll be posted on the NPTEL portal. You'll be also getting emails regarding that.
सर लेकिन जब डेट ख़त्म हो जाएगा उसके बाद आएगा तब तक तो सर हम लोग
No,
गलत भी जो होगा गलत
we are
ऑप्शन
not,
होगा वो सुधार नहीं पाएंगे
Mr.
सर
Harish. We cannot solve assignment problems. Uh, Suppose you are due to your assignment, say third week assignment is due. I cannot solve the third week assignment in the class and give you the answers because there is no point in uh, solving questions in the session and then students or participants going and putting the answers there. There is absolutely no point doing such things. So and also we are completely we are informed not to solve assignment problems. Is that okay for you? That's
सर एक
how.
बार मिला लेते सर
No, we are not. It's simply the rules that we need to oblige. That's it. Is that okay? We absolutely we cannot do it because we suppose an assignment is given to you and we discuss the solutions and then there is no point in grading again, right? You understand the logic? We
सर
suppose
पढ़ने में हम
the
तेज नहीं है
third week.
सर
Sorry.
सर वीक थर्ड का नहीं सर
Hmm.
वीक फर्स्ट वाला ही वीक फर्स्ट का करवाइए ना सर वो 8 तारीख तक ही लास्ट डेट है सबमिट करने का बस एक बार थोड़ा सा और मतलब आप आप जो प्रोबेबल आंसर बस एक बार बता देते हैं हम लोग बनाए हैं बस मिला लेते उससे
No, no, Harsh. This is not going to happen. That I can only take some of the problems from different textbooks or previous year questions, and I can uh, uh, discuss it in the class. But I am absolutely not encouraged to discuss the assignment problems before the answers are given because there is no logic discussing the answers or telling the most probable answer and then the students giving assignments and then grading it. I hope you understand it and we'll move forward. Right. Okay. Uh, the first question. In a planar kinematic chain, we have two statements. The first one, a revolute pair eliminates 2 degrees of freedom. And in statement 2, a prismatic pair allows 1 degree of freedom. So choose the right option from the four. I'll give you a couple of minutes to think over it, and I'll I'll tell you the solution. Okay, one of our friends says, Harshvardhan says, the answer is C. Okay, any other answers? They need some more time, or shall I discuss?
We start discussion, sir.
Okay. Uh, so let us consider an xy plane, and for example, we have a body, and say we mark a point P. So the degree of freedom for this body can be degree of freedom is 3, that is x, y, and theta coordinate. So using these three degrees of freedom, we are going to fix the point P on that rigid body. Now let us extend the discussion when two bodies are connected by a revolute joint. That was revolute, right? Yeah, revolute pair. So when these two are connected with a revolute joint, suppose we have, I will denote the number of links with numbers and number of joints with alphabets. Okay. So we have first link here, second link here, the number of joint. This is the joint A. Okay. So degree of freedom for a spatial mechanism, that was already mentioned in the question, that it is a spatial kinematic chain. So degree of freedom is 3 times of NL minus 1, that is number of links minus 1, minus 3 times of Nj plus sigma Fi, that is degree of freedom of each joint, where I runs from 1 to Nj. Okay, this is the formula for degree of freedom for a spatial mechanism. I'm going slow because this is our first class. So if you put the number of links as 2, number of joints as 1, because we have one joint and 2 links, so it comes out to be degree of freedom as 1. So the first statement which says that a revolute pair eliminates 2 degrees of freedom, that is right, because initially this had a degree of freedom 3, and when you connect these two bodies with a revolute pair, the degree of freedom is reduced to 1. Okay. Any questions here? Okay. The second statement, a prismatic pair allows 1 degree of freedom. So this is a straightforward one. Uh, a prismatic pair can be denoted like this, something like this. So we have a sliding motion or translatory motion. So the degree of freedom for this one is just 1. We have only translatory degree of freedom. So for a prismatic pair, uh, it allows only 1 degree of freedom. So both statements are correct. So the correct answer is C. Any questions? Okay. Uh, Before we get into uh, defining what a lower and a higher pair is, I like to define lower and higher pairs. Lower pair is the one where you have area contact, and higher pair is the one where you have a point contact. I'll give you few examples of uh, lower pairs and higher pairs after this problem. A ball and socket joint has dash degrees of freedom and is a lower or a higher pair. What is it?
Higher pair.
Any answers? Okay. Okay. We have A, B, and C. Three answers here. Okay. One more answer. A. Okay. This is straightforward or one which we have directly need to answer. So a ball and socket joint has 3 degrees of freedom, x, y, and theta. So the first one is quite simple, 3, and it is a lower pair because it has area contact, because the ball sits in the socket and it has area contact. So it is not a higher pair, it is a lower pair. So the correct answer is B. It has 3 degrees of freedom, x, y, and theta, and is a lower pair, not a higher pair. The participants who have told A and C, uh, they need to correct their thing. Okay. So I'll give you few examples from the textbooks where they define lower and higher pairs. So this these we are going to deal with predominantly with these lower pair joints. So a revolute joint or a hinge joint or a turning pair joint. So these all are denoted with this symbol. We should be well versed with the sketch symbol also, because we are going to draw kinematic diagrams in the later stages. So these all are lower pair joints. That means they have area contact with them, and also a sliding pair or a prismatic pair we can call. So it is also having a degree of freedom 1. Even revolute joint has a degree of freedom 1, and it is also a lower joint. A screw joint or a helical joint, even this is a lower pair joint. Okay, and this also has a degree of freedom 1. So this table is going to be very useful for us because uh, unless we have a good hands-on experience or good uh, memory with these pair joints and degrees of freedom for each pair joint, it will be difficult for us to solve the numerical problems in later stages. Cylindrical joint, it has 2 degrees of freedom. One is translational and one is rotational. So it has 2 degrees of freedom. A spherical joint or a ball joint, you can call it uh, you can also call it uh, I mean a ball and socket joint. So it has 3 degrees of freedom, and it is also a lower pair as we have discussed in the previous section, and also a planar joint. It also has 3 degrees of freedom, one translational, one rotational, and the other is also a translational. So two translational and one rotational. So a planar joint also has three uh, degrees of freedom. There are
How to
some,
classify the 1 minute, sir? How to classify the lower pair and higher pair?
sorry,
Point contact, surface contact, line contact. In this manner only we have to classify the lower pair and higher pair.
can you repeat your question again?
Sir, how to classify the lower pair and higher pair, sir?
Okay.
According to the contact surface only we
Yeah.
classify.
Yes.
Uh,
The classification
in
is
three
only based on
category will be there. One is area contact, surface contact, line contact, point contact.
in lower and higher pairs. What we are going to say is point contact uh, and area contact. The
Okay, sir.
ones which have area contact we are going to call as lower pair, like spherical joint, ball and socket joint, etc. They are lower pairs,
Okay.
and these all are lower pairs. In fact, for the higher pairs, I'm going to show you.
Okay. Okay, sir. Proceed. Proceed.
The higher pairs, suppose we have a cylinder which rolls without slipping. This has a degree of freedom 1. I would like to caution you that if there is rolling with slipping, we have 3 other degrees of freedom. So if a cylinder is rolling with slipping, it has 4 degrees of freedom, whereas if it is rolling without slipping, then it has only 1 degree of freedom. So the textbook here mentions for the condition where there is the cylinder rolls without slipping. So it rotates about its instantaneous center, that we are going to see in at a later stage. So this is one of the example of a higher pair where there is only a point contact at the surface, and also cam pair, where a cam is uh, rolling to and fro on a follower, and also a rolling ball or a sphere without slipping. We have 3 degrees of freedom, and a ball in a cylinder, we have 4 degrees of freedom, which can rotate which can rotate about any axis through 3 axes and one sliding. So totally we have 4 degrees of freedom when a ball is in a cylinder. And spatial point contact, this is a special uh, pair where a body can rotate about any axis and can slide in any direction of its plane. So it can't go down. So 1 degree of freedom is lost. So the other degrees of freedom x, y, if z degree of freedom is lost, I can say that x, y translational freedoms remain intact, and theta, phi, and psi angles remain intact. So we have 5 degrees of freedom here. So as you see in all these pairs, the contact is only a point contact. Uh, there is no area contact in any of these uh, pairs. So such joints are called higher joints. And in our previous section, where we have a ball inside a socket, there is area contact. So such pairs are called lower joints. If you want, you can Also go through one of the textbook which I have put the source, Kinematics, Dynamics and Design of Machinery by Waldron. You can have a look at it. If there are no further questions up to this point, I would like to encourage you to draw a kinematic diagram of this mechanism. Uh, this is a planar mechanism. Some of us might have questions about this joint and this joint. So that's why I am mentioning a priori that it is a planar mechanism. So motion is only in parallel planes. So I'll give you maybe 3 or 4 minutes to draw a kinematic diagram of this mechanism. So a kinematic diagram, you might have followed it in the lectures also. A kinematic diagram is a line diagram that helps us to identify the number of links and their joints. In kinematic diagram, for the time being, we are not going to give any respect to the dimension of the links. So the main purpose is to identify the number of links and number of joints. That's the main agenda of drawing a kinematic diagram. So go ahead, I'll give you 3 to 4 minutes to draw. Uh, then I'll show you uh, the diagram of it. If you have completed, you can just comment saying that uh, it is done. Maybe I'll give you a couple of minutes more to complete.
Sir,
Yeah,
am I audible?
yeah, please go
Hello.
ahead.
Yes, sir. I just have one doubt.
Yeah,
In ball and socket mechanism, the point of contact is either line or point, right?
no, it is area contact. The ball goes and sits into the socket. The best example for it uh, is our knee joint in our leg, in our limbs.
Okay.
There will be a ball in our knee, and the
Mm-hmm.
socket is going to hold that ball. It's a ball and socket joint, so it's an area contact and not a not a point contact.
Okay, okay,
Yeah,
okay, sir.
yeah. I hope everyone has given a try uh, of drawing this kinematic chain. So, uh, after drawing the kinematic diagram of this mechanism, we need to identify the number of links and the number of joints. I hope everyone has given a try. Okay. So, this is the kinematic diagram of that mechanism which I have shown in my previous slide. So, let's get started. Uh, so, the aim is to find out the number of links, number of joints, and the type of links, whether it is a hinge joint or a pin joint, etc. etc. So, I am not going to give reference to the dimensions, of course. So, I'll start from the top. I have one joint here. I have one link connecting these two joints. I have this. Okay. This is connected to ground. Okay. Okay. This side is done. So we'll come to the next side. I've told you that this is a planar mechanism, so don't think that this comes out of the plane. So this also we can represent it with a hinge joint or a pin joint. We are going to connect it with one more link, and okay, this is also a R that I will mark later, and we are having a sliding motion here. This is also our ground. So ground, it is hatched. Okay. So first, I am going to denote links L with numbers, and joints, I am going to denote it with alphabets. Okay. So this is the convention that I would like to follow, so that uh, we don't get confused between demarcating links and joints. So I'll first start with links. So ground is one link. I'll mark one. Uh, Ground remains constant everywhere. So here also it is one. We shouldn't make a mistake of making other link here. So we have marked one ground. So next we are going to mark this link. This is 2. We have another link here, that is 3. We have another link here, that is 4, 5, and 6. So the number of links here are 6, and we are going to identify the joints. So this is a revolute joint, R joint. So this is also a revolute joint. This is a pin joint. This is also a pin joint or a hinge joint, you can call. This is a revolute joint, and this is a prismatic joint or a sliding joint. Okay. uh, PR. So I have A, B, C, D, E, and F. So I have 6 joints in total for here also. So you can go ahead and calculate the degree of freedom for this joint also, because you know the degree of freedom for each joint at each joint is also 1. So sigma Fi, the formula which I have shown you, that comes out to be 6. So you can go, of course I have not asked you to uh, uh, evaluate the degree of freedom. That is nothing but 3 times of number of links minus 1, that is 5, minus 3 times number of joints, that is 6, plus sigma Fi, that is 6. So this is your degree of freedom for this planar mechanism. So we have 6 links, 6 joints, and this degree of freedom 15 minus 18, so minus 3. So degree of freedom for this is 3. Any questions here? Is everyone comfortable in drawing a kinematic diagram for this mechanism? In fact, the textbook already had mentioned uh, the number of links by the numbers too. So, but it's an exercise for us. Okay. If no one has any other question, we can proceed forward and draw the kinematic diagram of this mechanism and gives the number of degrees of freedom. I'll give you 3 to 4 minutes for even this, and this is also a planar mechanism. And uh, after drawing the mechanism kinematic diagram, please let me know what is the degree of freedom that you are getting. The people who have completed, they may just unmute and answer, because it is little difficult for me to switch between tabs and see who has completed or who has questions. So I'll encourage you to unmute and ask. Okay, has everyone got enough time to solve? Can you tell me what is the degree of freedom for this mechanism? Okay, I'll go ahead and uh, if you need some more time, you can stop me, or I'll go ahead and draw the diagram. Okay, so let me start with let's start with these two prismatic pairs. I have two here. Okay, these two are done. I have this joint. Somebody has posted a question or something. I'll get back to it. Let me draw this. This is done. Uh, Link this is done. I have this. Okay. So let me mark uh, the same notation I would like to follow. Uh, Numbers are for links. Joints are going to be represented with alphabets. This is also a planar mechanism. So ground is going to be given the first link. Okay. So this is 1. The next link is 2 here. This is my third link, 3, 4, 5. Okay. So number of links here are 5. Uh, Let me mark uh, the joints. I have A here, which is a revolute joint. I have B here, which is a prismatic joint. I have C here, which is also a prismatic joint. D, which is a revolute joint. And E, it is a hinge or a pin joint. So number of links are 4. Number of joints, I'm sorry, 5. Number of joints are also 5. So for the planar mechanism, sigma fi, that is degree of freedom at each joint, where I is equal to 1 to nj, that is 5. Sigma f5 is also 5. So to find out degree of freedom, now we have degree of freedom is nothing but 3 times of number of links minus 1, that is 4 minus 3 times 5 plus 5. So 12, 17, 17. So degree of freedom of this mechanism is 2. Any questions here? Can we go forward?
Yes.
Okay. Uh, we have one more question here uh, to find the degree of freedom of this mechanism. So to find out the degree of mechanism, first step would be to draw the kinematic diagram for this. Identify the number of links and joints, and then find out the degree of freedom. I'll give you 3 minutes or 4 minutes again, uh, and you can tell your answers. Any answers for the degree of freedom?
2 minutes.
Sorry, you said 2 minutes, or you said the degree of freedom is two?
No, no, 2 minutes.
Okay. Okay. We have two answers. Two of our friends has 2 degrees of freedom. Okay. Any other answers? I'll give a minute or more, uh, and then I'll draw. Okay. I have a ternary ring here. Start with that. It's connected by hinge. Fine. I have a revolute joint here. Revolute joint here. Okay. Okay. I have one more hinge joint here. Okay. The convention will follow the same old convention. Numbers I'll write for links. Uh, for joints, I'll be writing the alphabets. Okay. So I'll start with giving numbers. Uh, Ground, we'll start with ground always. So link number one, that is ground. Okay. Next, this is link two. This whole link from here to here. Next, three, we have one ternary link here, that is link 4, and one more link here, 5. So the number of links here are 5. Okay. Now we'll denote uh, the joints. So I have a hinge joint here, A, which has 1 degree of freedom. Next I have a revolute joint here, B, which has 1 degree of freedom. I have one more revolute joint here, C, which has 1 degree of freedom. One more hinge joint or pin joint you can call. It has 1 degree of freedom, and D, and this is E. And uh, I have one more joint here, F. So, uh, so my number of joints here are 6. So the degree of freedom is nothing but 3 times number of links minus 1, that is 4, minus 3 times of number of joints, that is 6, plus sigma fi, that is 6. So the degree of freedom for this mechanism is 1.
Sir, one doubt.
Yeah. No, sorry, this
Sir,
is
the one
2.
which is connecting.
This
Yes,
is
sir. So the
2. Yeah.
one, the link which is connecting from 5 to 2, isn't
Okay.
there a slider inside?
This one you are talking about.
Yeah, yeah, inside that.
This is a
So,
solid link and it is not a slot. So it doesn't have a slider motion here. It is a solid
oh,
link. It's not a slot.
okay, okay. I mean, I consider it as a slider. So, okay,
Yeah.
no problem.
Oh, I'm sorry. This is uh, 12 plus 6, 18. 18 minus 18, 0. So this is a 0 degree of freedom mechanism. So this has a degree of freedom 0 and not 2. I'm sorry. I made a arithmetic mistake. This has 0 degrees
Sir,
of freedom. Yeah.
excuse me, sir. Hello.
Yeah.
Sir, how can you take EFI, sigma F suffix I, you take 6?
Yeah. Sigma fi is the degree of freedom at each joint. So we have 6 joints which are named with alphabets A, B, C up to F.
Okay.
So each joint we have a single degree of freedom. All these are hinge joints or a revolute joints, which all have a degree of freedom 1. So sigma fi comes out to be 6.
Okay, based on joints, number of joints.
Yes, at each joint,
Okay, sir.
So this will sigma fi contribution from each joint is this is 1, uh, this is 1, B, this is 1, this is a revolute joint, so this has a degree of freedom 1. So D it is also it is a pin joint which contributes to 1 degree of freedom. E again it will contribute, it has 1 degree of freedom 1. Then F also has 1. So if you do a summation from A to F, which all have single degree of freedom, so your sigma Fi comes out to be 6.
Okay, sir. Sir, if at point at the joint B there is a cam and shaft connection,
Uh, uh,
if there is a cam and shaft connection, then
at
what is the Fi?
Okay, you have a cam and follower connection. So what is the degree of freedom? So for a cam pair which slides on a follower, it has 2 degrees of freedom. So if I'll show you one more, that was your question, right? Am I answering it?
Yes, sir.
What you decide?
Yes, sir. Yes,
Yeah.
yes.
So I have one more example which shows multiple degrees of freedom at one joint. Uh, for
Okay.
your question, where if one joint is a cam and follower, so the degree of freedom, as I have mentioned here, it is 2. So when you take Fi for that joint, you are going to write 2 there.
Okay, sir. Okay.
Okay, so that's the reason why
Okay, sir.
I made a table of this, so that we have a proper clarity on degrees of freedom for every joint. So we need to have this at the back of our hand, so that we don't make mistakes.
Okay, sir. Thank you, sir.
Any questions in this problem?
Sir, in this equation to find the degrees of freedom,
Yeah,
so how to identify this as sigma Fi? Degree of freedom of each link you have to write, sir.
yeah.
Last one.
As I have mentioned, so links I have mentioned it with alphabets, right? So here we have one hinge joint that I have
Mm,
denoted it with A. Okay,
mm,
so that has 1 degree of freedom. Okay, that
okay.
is that I have circled it here with 1. Okay, so
Mhm.
next at B we have a revolute joint which has 1 degree of freedom.
Okay.
Okay, at C it is also a revolute joint, it has 1 degree of freedom. At
Okay.
D I have one hinge joint or a pin joint which has 1 degree of freedom. Similarly
Okay.
E and
Okay.
similarly F. So
Okay.
sigma Fi is
Sigma Fi.
maybe participants are having some questions of definition of Fi. So
Fi.
that is the degree of freedom of ith joint. Okay, ith joint is nothing but it runs from I is nothing from 1 to number of joints. So in case uh, here in this problem all are having 1 degree of freedom, so we have got the summation as 6. As
Okay.
your friend asked me a question, what if a cam and follower pair is there instead of a R pair or a prismatic pair? Then we are going to write the degree of freedom for the at that joint as 2 instead of 1.
Thank you, sir.
Yeah, is that explanation satisfactory?
Yes, sir.
Yeah,
Sigma Fi have note on Sigma Fi.
yeah,
So degree of freedom of each joint. I understood this.
yes, correct.
Thank you.
Any other questions here?
Sir, this equation is developed by what is this equation called as, sir?
This is the degree of freedom for a formula of degree of freedom for a planar mechanism. Okay.
Uh,
Uh,
Scientist name Grubler criteria like that.
no, this does not have any criteria as such like that.
Okay.
But it has some explanation of how we have arrived at this expression. Maybe you can watch the NPTEL videos delivered by Professor Anirvan Dasgupta sir. Uh,
Okay.
he derives the uh, expressions of how we are getting this expression. The criteria, which Grashoff's criteria, those things
Grasshopper.
are going to come later and not at this stage.
Okay. So this is the fundamental equation to find degrees of freedom.
Yes.
Thank you. Thank you.
Any other questions? Okay. If there are no other questions, we will jump to the next problem. This is little tricky. There is one catch. Uh, we have a planar mechanism. We want to find the degrees of freedom when one of the joint is a coincident joint. Okay, that means uh, 3, 4 and 5. Links 3, 4 and 5 uh, have a coincident point. I'll give you 3 to 4 minutes so you can try it out.
Sir, is this video session is shared again or not,
So,
sir?
I didn't follow your question.
This interaction session
Yeah,
will be shared to us, sir, later. This
yes,
video
it will
link.
be shared. It will be
Thank you,
shared.
sir. Thank you.
I'll be uploading it. You'll have access to it. Any answers?
One day,
Sorry?
one.
1. Okay. One of our friends says the degree of freedom is 1. You need some more time to try? Others? Okay, can I discuss? Okay. They have already marked the links, but in practice, we should be able to do it. Uh, so this is link 1, that is ground. This is link 2, numbered with 2, 3, 4, 5, and 6. So the number of links here are 6, and we are next going to find out the number of joints. Okay, so this is joint A, which is a revolute joint having 1 degree of freedom here. Okay, I'll maybe circle it. This is one more revolute joint B, which has 1 degree of freedom. Okay, the catch is here we have two joints here, C and D. Okay, then we have E here, which has single degree of freedom, F here, which has single degree of freedom, G pin joint, which also has 1 degree of freedom. Okay, so the catch here is when joints are coincident, we are going to consider only the joints as 2, and the link will remain as intact. There is no confusion with respect to number of links. Only the joints we are going to consider it as 2. Okay, and also this link 3, 4, and 5, this we are going to consider it as 2R, that means 2 revolute joints. Okay, so as a result what we get is we get number of joints as 7. I'm sorry, this is a single revolute joint here, uh, and sigma Fi comes out to be 6. Okay, so the degree of freedom, once we identify this, it is an easy job of putting it in this formula. uh, the degree of freedom comes out to be 1. Only the number of joints we are going to consider it as 2, but the degree of freedom at that point will be 1. Is this okay for everyone?
Sir, on substituting, we are getting zeros, sir. This one.
uh, 3 times of nl minus 1, that is 3 times of 5, 5, so that is 15.
Minus.
15 minus number of joint 3 times 21, plus 6. Okay, degree of freedom is 0. Yeah,
Sir,
yeah.
C and D have 2R, right? So if there are 2R's, then A, B, D, G, F will have 5 plus 2R. So it will be 7, right?
Just a moment. uh, uh, 3 and 4 is one R joint. 3 and 5 will be another R joint. So yeah, this is 2 revolute joints. This comes out to be 7 here.
Then it is 1.
Yeah, yeah. I made a mistake here. I'm sorry for it. Uh, this constitutes 2 revolute joints. Okay, so
Sir,
Fi comes out to be 7.
7.
Sigma Fi comes out to be 7 and not 6.
Sir, is A, E, G are same joint, sir?
A, E, and G. Yeah, they are pin joints. All are pin joints. all have 1 degree of freedom.
Sir, is pin joint and roller joint both are same terms, sir? Same, sir.
Uh, pin pin is the one where it is attached to ground. Revolute is if it is attached to another link. But
Okay.
both will have a single degree of freedom.
Okay.
It is pinned to ground. The other one is revolute joint, which is connected to other link.
Okay.
Yeah.
Sir, if degree of freedom becomes zero, that means it is a rigid body.
Yes, it is a rigid body. So there is no transfer of motion. Uh, that
Okay, sir.
we can tell it at the surface, but it is not always true. There are some exceptions for it. That exceptions we will get to know maybe after 3 or 4 lectures, 3 or 4 sessions. I'll show such anomalies also.
Okay, sir. Thank
Okay. Okay. I think I have missed one question here. Okay. It is later. Okay. So I want to find out the degree of freedom of this spatial mechanism. Till now, what we have done were planar mechanisms. Now, this is a spatial mechanism. So, the formula of degree of freedom, where we multiply it with 3, gets substituted with 6 because we have 3 other degrees of freedom.
Sir, can you show the question, please?
Okay, I'm sorry. Any answers?
1 dear.
Okay. 1 degree of freedom. So what is sigma Fi that you have got?
7.
Okay. Okay. Good. Do you need some more time or shall I discuss the solution? Okay. 1 degree of freedom. 1 degree of freedom. Okay. So we'll draw one kinematic diagram for this. I have a prismatic joint or a sliding joint here. I have one sliding joint here. Then I have one spheric joint here and one cylindric joint here. This is attached to ground. Okay. So I'll name the links first. This is my link 1, link 2, 3, and this is ground 4. Okay. So the degrees of freedom now. I have a sliding motion here. So I have 1 degree of freedom. I have a sliding motion here. So the degree of freedom again here is just 1. This is a spheric joint, spheric joint. So I have 3 degrees of freedom here. This is a cylindrical joint. I have rotation as well as translational degree of freedom. So 2. So my number of links here are 4. Number of joints are also 4 because 1A, this is A, this is B, this is C and D. So number of links are also 4 and summation Fi. People were asking me how to take Fi, right? So this is 1, this is another one. So 2 plus 3, 5, 5 plus 2, 7. So Fi comes out to be 7. So the degree of freedom formula for spatial mechanisms is 6 times of number of links minus 1, 6 times number of joints plus summation Fi. So if you plug in the values, 6 times 3, 18, 18 minus 24 minus 6, minus 6 plus 7, 1. So degree of freedom is 1 for this. Any questions?
Sir, please explain the FI 7. How we can get 7, sir?
7. Okay. So link 1, this is link 1, which has a translational degree of freedom, that is only 1. Link joint 2, I'm sorry, joint 2 has a translational degree of freedom, that is 1. This is a spheric uh, joint where the degrees of freedom for spheric joint is 3, and this is a cylindric joint where we have 2 degrees of freedom, one is rotational and the other is translational. So 1 plus 1, 2, 2 plus 3, I have 5, 5 plus 2, that is 7. Is the answer
Okay.
satisfactory or you need some
Okay.
more clarification?
So first one is degree of freedom translation comes under 1 degree of freedom.
Yeah,
Second one is second joint degrees of freedom is 1.
yes,
For the spatial, sorry, this
spheric joint,
3 degrees of freedom here.
correct.
And the fourth one is cylinder manner. This is
Yes,
considered yeah,
yes,
2.
we have 2 there, cylindric joint.
Okay, sir.
So 3 plus 2 plus 1 plus 1.
7. Okay. All right.
Yeah,
No need to bother about the fixed position. 4. Okay, sir.
no, no,
Clear.
that is that doesn't come under joint. That is
So
a
as
link.
per the joint only, we can consider the degree of freedom.
Yes, joints, only joints are to be considered for degree of freedom.
Okay, right. Thank you. Thank you.
Any other questions here? Okay, uh, we'll go to the next uh, easier problem. By this time, we have got some hold on links and joints. So this is an easier one. We need to find the number of ternary links in the mechanism shown. Can you just see how many ternary links are there in this mechanism?
One.
Okay, one of our friends says it is 1. Any other answers?
2, sir.
Okay,
One
2.
with the ternary link and one more with the ground.
Okay, any other answers? Okay, this is one ternary link. Okay, and as our friend pointed out that ground is also one more ternary ring. As you see, uh, here it is connected to 2, and again this is also 1, so it is connected to 4, and again this is also 1, this is connected to 7. So we have 2 ternary links in this planar mechanism as shown. This is one, and ground is also one ternary link here. Any questions? Okay, we'll go to the last uh, problem of today's session. We want to identify the number of links in this mechanism. I'll give you few minutes of time. You can try it out before I tell the answer.
Sir, can you explain previous problem?
Oh, okay. So ternary links are one where uh, the link is connected to more than two. So if you consider uh, the link here, we have three links connected. So this link is considered to be a ternary link. Okay. Uh, the other ternary link is between is the ground, which is because the ground is connected to link 2. Again, this is also 1 because ground is always considered 1. Uh, the same link 1 is connected to link 4 and the same link is connected to link 7. So more than the ground is connected to more than uh, two links. So that's why ground is also a ternary link in this problem.
Okay, sir. Sir, if ground links are not in same axis,
If
then we will
sorry,
also
if
take it as
ground links are not in,
same axis. In this diagram, axis is same as
okay,
per ground
you are
link.
asking if it is not a planar mechanism.
Yes, sir. Yes.
Even if the ground are not in same axis, we are going to consider that to be a ternary link.
Okay, sir.
Yeah.
Okay, sir. Thank you, sir.
Yeah.
Thank you. Next problem.
Yeah. Any answers? Number of binary links in this mechanism?
So 5.
Okay. We have one answer, 5. Any other answers? I'll, I'll give you people a couple of minutes more, then I'll discuss the solution.
So one more link will be added. I think 6.
Okay. So one of our friends says the number of binary links in this mechanism are 6. Okay. We have two more answers, 7 and 6. Do you need some more time to try, or shall I draw the kinematic chain and show you? Okay. I'll go ahead. One. Two. This is link 4 and also 5. 6 here. These two are connected, so 7. This is link 8 and this is 9. Okay. So this is the kinematic diagram of the excavator mechanism that is shown here. So this is link number 1. This is one binary link. This is the second binary link. From here to here I have third binary link. Fourth and fifth, it is cylindric. Uh, there is a cylinder there. So I have two more binary links there, 4 and 5. The next one is this link, 6. One more, I have a binary link 7, and 8 and 9 are followed. So the total number of binary links in this mechanism is 9. Any questions here?
Sir, link number 3, isn't it a ternary link?
No, it is not a ternary link.
Is because it's connecting with three other links, right?
No, that's the reason it is not shown as a direct joint here. Uh, that's why I have shown it like in this fashion. It is not connected to the link here.
Okay, okay,
Okay, that's a binary link, not a ternary link.
okay.
Any questions in the session today?
Sir, one last doubt with the previous
Yeah,
question.
yeah, go ahead.
Yeah, not this one, the next one. No, the next, last one. Yeah.
Okay.
Uh, in your diagram, uh, there is one link which is connected to one more link, right?
I have
I mean to
erased
say
it.
in the
Uh,
bucket.
I have erased it. Can you help me point it out?
Yeah, sure, sir. Near the bucket,
Okay.
uh, when you have drawn the kinematic diagram,
This is one
there,
link, and
yes,
this is another link.
yeah. So that was an open chain, as of what I remember, but it should be closed one, right?
Yeah.
Because the
The
bucket.
the bucket will close it. The bucket I did not show.
Okay, so those are again interconnected, right? That link is interconnected, right?
No, you need not consider the bucket from. Okay, your question is, what about this one?
Yeah, that one too. Yes,
No,
exactly.
that is not going to be considered. It is directly connected to the end portion, end
End of it.
actuator.
Okay,
So
okay,
that is not going to be considered as a link.
okay, sir.
So you
Sir,
mean
what
it
about
is
the
relative
bottom?
motion?
Sorry.
You said that is a end actuator. That means there is no relative motion between the two elements.
Uh, with respect to this link, link number one and the end actuator, there is relative motion. With respect to this link and the end actuator, there is relative motion.
Okay, sir.
Okay. Is the explanation satisfactory? Any other questions in any other problems that we solved? Okay. Before we leave, since this is our first session, I would like to have a feedback so that in our next sessions we can engage more. So I'll ask you for an honest response. How engaging were these past 2 hours? Okay, on a scale of 1 to 5, uh, you can rate. Uh, okay, you can give me your honest response. 5 goes for most engaging, 1 goes for least engaging. uh, you can just give me a poll so that next subsequent sessions, for the next 7 sessions, we can work out in a much better way. Can you just go and give your polls, your answers? Okay, there are some questions here. uh, uh, Please give me assignment solutions. Yes, assignment solutions, they will be posted once the grading has been done. Okay. uh, very nice session. Okay. I have some can anyone make one WhatsApp group? It is useful for us. That's your uh, that is internal amongst yourself. Uh, okay. Uh, okay, you need some more problems. Sir, it's clear and good session. Okay. Next session, I'll try to get a few more problems. We'll try to solve them. Okay. Thanks for your attention.
Sir, just a minute, sir.
Yeah.
Uh, don't we have a session with Grashof criteria?
Yeah, we have it. Every
When?
week we are going to meet on the same time. Uh,
Okay, but I believe the I mean week two deadline is tomorrow.
for the assignment that you're talking.
Yes.
Yeah. So we cannot. Uh, 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 the next the this week was based on week one. So the next problems that we are going to solve will be based on week two content. So
Okay.
that's the way we are going to move forward.
Okay, sir.
Okay, I'm ending the session. Thank you.
Thank you.